Okay, hey guys, another week. Believe it or not, we're about halfway through the semester. Whoa, sorry, camera's freaking out. Can you believe it? We're already at like chapter 6. I mean, I guess we have a little bit farther to go, but for me, when we hit chapter 6 every semester, I'm kind of like, okay, we're like almost halfway through. So good job hanging in. We are going to do cellular respiration today, and this is normally a lecture that I do with a lot of class interaction. So I kind of have to see how it goes when I'm doing it remotely like this. But there's going to be a lot of vocabulary. And in addition to learning the vocabulary, cellular respiration is this process. So a lot of the things we've been doing so far have been kind of vocabulary and concept based. But cellular respiration and next chapter for photosynthesis, it's really more of process-based. So we have these steps that our body goes through. And the point is to take certain things from our environment and create energy, okay? So start over here, create energy. That's the point of it. And then we've got all these steps to make it happen. So kind of set your mind right now for having this be a process-based lecture this whole week and next week, and that hopefully will help you kind of not just be looking for key vocabulary words, but it will help you try to absorb the steps in the process and what's happening and why. Okay. Having said that, if at the end of any of these lectures you are feeling utterly and completely lost, don't worry. Reach out to me and we'll go over it. I have a cellular respiration YouTube animation video that I really like. It's like 7 minutes long that I've included with this module. So, you know, you can watch it at any point. I often suggest that you watch it before you get too far into these lectures. I mean, like if you watch today's lecture, then watch the cellular respiration video. And then after we go through all the steps, watch it again at the end. And it usually makes a lot more sense. Normally we do that together in class. Obviously it's not something we're going to do together like that, but I have provided that link for you. So without further ado, let's get going. Let me share my whiteboard, and I will start with some of the vocabulary I kind of told you about. Okay, so say what we're doing here. Oh, I'm losing all my stuff. Okay, so this is chapter 6, cellular respiration. All right, so here's a new term, aerobic. You probably know what aerobics mean, or aerobic means when it comes to exercise. But when we're talking about it in science, we're actually talking about whether or not there's oxygen. So something that's aerobic uses oxygen. Oxygen is required, or oxygen is present. So you can say that, you know, this something is in an aerobic environment. It means that there's oxygen in the environment. The opposite of that is anaerobic. Okay, anaerobic means does not use oxygen. Oxygen is not required, or oxygen is not present. Okay, so you'd say like space is an anaerobic environment. We don't have oxygen in space, right? Okay, so that's what these terms mean when we're talking about it in biology, and those terms will come up pretty regularly, okay? The next set of terms go together as well. Oxidation. Oxidation is the loss of electrons in a chemical reaction. And its opposite, reduction. And reduction is the gain of electrons in a chemical reaction. Okay, so I'm going to pause here for a second on the notes. Cellular respiration is going to circle all the way back to chapter 2 when it comes to remembering how electrons form bonds with other atoms and other molecules. Electrons are what's used to give off energy for this process of cellular respiration. So we're going to watch electrons moving for a while throughout these steps. And again, if this isn't making sense or if it doesn't make sense at the end of today's lecture, it's totally normal. You kind of have to get all of the pieces and then put the pieces together, you know, to get the whole picture. So these are just pieces right now, so don't stress. Okay, the terms. I know it's weird. People, you know, we all think reduce means to lose something, to lessen something, and yet here it's gaining electrons, right? Whereas oxidation is losing electrons. That's because this term reduction actually is referring to reducing the overall positive charge of an atom, or reducing from a neutral charge. So when you think about the word reduction, you got to think about it reducing the positive charge because it's gaining electrons. And when an atom picks up more electrons, it becomes more negative. So it reduces the positive charge on the atom. That's where the term reduction comes from for this process. Okay. All right. So what is cellular respiration? Cellular respiration is the aerobic harvesting of energy from organic sources. Okay, so let's look at what all of these terms mean here. Switch over to my. So aerobic. We already know that this term means oxygen is present, right? So we have O2 present, needed. That means we know oxygen is going to be involved in this process of cellular respiration. Aerobic harvesting of energy from organic fuel sources. Organic. Well, organic is carbon-based, meaning we're looking at things that are part of living compounds or compounds that you'd find in living beings or living organisms, whether that's plant-based or otherwise. So what we have here basically is we're going to need oxygen and we need a fuel source, or that we would get from like food. So cellular respiration has an equation, and yes, you do need to know it. Okay, so let me remind you here for just a second how we look at how we read chemical formulas. I'm going to come up here and rewrite part of this. Okay, so again, this whole thing right here is one molecule. We know that because the letters are all written on top of each other. There's no space, there's not a plus sign in between them. We know that then what is in this molecule is carbon, hydrogen, and oxygen. Then to find out how many atoms of each, we look at these numbers here, the subscript, okay? So there are 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms in this big molecule. Over here, we have both a prescript, I guess, if you will, and a subscript. We know that this has oxygen in it, and there are 2 molecules of oxygen in this. How many of those do we have total? There are 6. So there's 6 groups of 2 oxygens each. Okay, so if I come back down here, this big molecule is glucose. Okay, so in glucose we have 6 carbons in a single glucose molecule, 6 carbons, 12 hydrogens, and 6 oxygens. Okay, remember that glucose is a monosaccharide or a simple sugar. Kind of see how all the chapters that we've been going over until this point, how they all build on each other, right? Okay, and then this right here is oxygen gas. This is the oxygen gas that we breathe. And so for this equation, we have 6 molecules of oxygen gas, okay? I think I told you before, but again, I'll just remind in case, there's not an equal sign for equations in chemistry. The arrow means yields. That's what you get out of it, okay? And what we get out is this over here. Carbon dioxide is CO2. There's 6 molecules of it. And of course, you notice we've got, actually go like that, water. And again, 6 molecules of water. Okay, so basically, another way to write this equation, although you do need to know the actual chemical one, but what we basically have is glucose plus oxygen gives us carbon dioxide water, and ATP, which, as we know from last chapter, is our energy. Oh, squeeze it in over here. Okay. All right. So let's look back up here at our definition for cellular respiration. We have aerobic harvesting of energy. Well, here's the aerobic part in our equation. It's the oxygen. Of organic fuel sources. Here's our organic fuel source. It's glucose. Okay. Get carbon dioxide and water plus energy that comes out of it. Okay. Let's pause in the notes this part for a second. And let me dive over here. All right. I'm going to say we're going to annotate this. So let's go back to oxidation and reduction for a second. If you remember, oxidation again is the loss of electrons and reduction is the gaining of electrons. These go together in oxidation reduction reactions, or people combine them and call them redox reactions, which is putting reduction first. So it'd be like reduction, oxidation, redox reactions. Okay, why do these happen together? Well, because electrons can't just disappear, right? So if one electron is being lost, or if one atom is losing an electron, that electron has to go somewhere. It's not disappearing. That means another atom is picking it up. So while one is reduced, the other is oxidized, and vice versa. So if we look here, maybe, come on, little pen. Okay, so if we look over here, we have molecule A, okay, or right there. And right now it has an electron, but it's going to be losing that electron to molecule B. When it does, A is oxidized because it has lost its electron. It doesn't have it anymore. And B is reduced because now it's carrying it. Okay, so lost the electron, and this guy gained it. Or reduced the positive charge because now it's got an extra electron. So if we labeled these over here, this one is currently oxidized, and this is reduced. Okay, so these redox reactions, these electrons moving from one atom or from one molecule to another, happens continually. Because again, you can't have that electron go nowhere. Okay, so when one loses it, another one gains it. Okay. This is an important part of cellular respiration because this is where energy is going to come from, is from this constant transfer of electrons back and forth. And you'll see that in the steps that are coming up. Okay. P.S. Don't flip out on the slides. I know they're busy, but I'm going to walk you through how to read them. So I tell my classes this every semester, again, usually just in person so I can see your faces, but don't freak out. And I've said it 100 times, and I'll keep telling you this because as you see a lot of the diagrams and the images I'm going to use, it's a little bit overwhelming at first, but you're not allowed to freak out. If you're still completely lost at the very end of all of this lecture, or this week, you still can't freak out, but then you can, feel like let's talk. What was I going back to? Oh yeah, I'm going back to my whiteboard, and I'm going to clear it. Okay. So cellular respiration is going to, it has 4 steps in it that I'm going to go over. Some textbooks put it as 3 because they kind of say that one is a sub-step of another, but honestly, when I teach it, we're going to go with the 4-step approach. It makes it a little more clear, especially at this level. So these are the steps: glycolysis, pyruvic acid grooming. Some texts call it pyruvic acid oxidation. There's that word oxidation. We know there's electrons moving. Citric acid cycle. And the electron, which when I'm writing it out or typing it, I'm going to abbreviate ETC because electron transport chain. That's all that. Each of these steps, of course, has little steps, sub-steps, because why not? Why not? Okay. Switch back. So some things to go over here. Glycolysis takes place in the cytoplasm of the cell. And yes, these are notes you need if you're writing them down. And it is anaerobic. Okay, that means that there's no oxygen required for this step of glycolysis. Okay, interesting. So it takes place in the cytoplasm, it's anaerobic, and this step actually requires ATP. So this step is going to require an energy input for the rest of the steps to happen. Okay, and that's unique to this step, as are these other parts, because these are going to be happening in the mitochondria, are aerobic and a make ATP. I say make ATP only because glycolysis, you're going to get a little bit of ATP out of it, but you have to put energy into it first. So, you know what, let me just change how I say this for a second. Oh, I hate when it does that. I was going to say it does not require ATP. And again, this was glycolysis. And then I had pyruvic acid grooming. Citric acid cycle, and the electron transport chain. Okay, all right. You're freaking out yet? Or are you just like crying a little bit inside because you're like, I don't want to know this and I don't really care and I'm so sad? It's actually interesting, although to be perfectly fair, when I was an undergrad, even though I was majoring in biology and I had to go through cellular respiration as an undergrad, the only thing I hated worse was photosynthesis, I'm not gonna lie. Now I'm like, it's amazing and I love it. But it felt really tedious as an undergrad. So not worry, you will get through it. Now I'm going to go back to my PowerPoint. Okay, let me talk you through what we're looking at here with this. Because on a lot of these slides, there's actually only some things that you really need to know, which is why I tell you not to get too upset when you see them, because you don't need to know everything that's on here. So here's glycolysis that we talked about. And again, this is going to be anaerobic. It happens out here in the cytoplasm or the cytosol. The difference between these two words is a slight technicality. Cytosol is supposed to refer to like the liquid itself, and the cytoplasm usually is referring to the liquid with all the organelles in it. It doesn't matter in this course. Then we have the mitochondria. And this is where we have, this is an older name for the citric acid cycle. Citric acid or Krebs cycle. We also have pyruvic acid grooming that's going to happen in here, although this one isn't going to show it. And then the electron transport chain. Okay, so right now you can ignore some of these other things. This is just showing glycolysis is outside the mitochondria and the rest is inside the mitochondria. Do I have my, I don't. Hang on a second. I want my mitochondria picture. So let me come over here. I'll use this one because it's the one that I use in lecture, in my PowerPoint. Okay, so we're looking here at our mitochondria. And I told you I'd talk a little bit more about its shape, or its structure, I should say, when we got to this part with cellular respiration. So here we go, I'm going to talk about it. Remember that the mitochondria has this inner membrane called cristae, and it's these foldings of the membrane that go back and forth, and you can see them here, right? All of this. And then you can remember that the fluid inside is the matrix. Okay, well, what are all these inner foldings for? What's the point? So, you've been to Disneyland, happiest place on earth, fight me over it, I'm ready, let's go. Ever been to Disneyland, or if you haven't, to some other amusement park, what happens with the lines? So there's this awesome ride, it's popular, and everybody wants to be on it. What does the amusement park do with the lines when people line up? Well, if this is the ride, it wouldn't make much sense. Like, let's say that this is Space Mountain at Disneyland. It wouldn't make much sense if this is Space Mountain and the line is just like this long straight line that would run out through who the heck knows where, the rest of Tomorrowland and out by the Matterhorn or whichever direction it goes. You just have these long lines for all the rides that just go straight back at people not being sure what line they're in and what they're waiting for, and it would just cause this massive traffic jam of people, right? So that's not how amusement parks do rides. Lines for rides. What do? They do like this thing. You're like, oh, I'm almost there to the ride. And then they're like, nope, just kidding. You're going to go over here and then you're going to do this and you're going to do it again. And okay, now you're finally at the ride. Anyway, right? So they do this twisty-turvy, curvy, back and forth, in and out type thing because it takes the available room and it maximizes it, right? So they can have a relatively small area where their line is going to be, but they maximize that area by making the line do all these wonky things, right? We've all been. Mitochondria does the same thing. The inner foldings of the membrane in the mitochondria is basically doing the same thing that these crazy lines at amusement parks do. It's maximizing surface area. Why do we need all the surface area? Because this is where the ATP is produced. Remember that mitochondria is the powerhouse of the cell. This is why, because the power, the ATP, is generated here. And we need as much of this membrane as we can get, because the more we have, the more ATP we can generate. Because it's not that you're getting one ATP per mitochondria, you're getting multiple, dozens, hundreds of ATP per mitochondria, okay? And the more of this membrane we have available, the more places that cellular respiration can happen and the more ATP can be pumped out, okay? That's why mitochondria is like this. All right. So I'm going to stop this lecture here because I'm going to start going through the steps of cellular respiration in the next lecture or two, and these are probably a little bit easier if I do them in smaller bite sizes because, again, it's not just vocabulary based, it's process based. So I'm going to stop this one here, and then I will have another one up for you in the next week or so. All right, guys, thanks.